Okay, welcome to question 2. We're doing question 2 in the mid-year exam. Just going through the answers and the question and answers. And this is in question 2 in this specific mid-year exam was our trigonometry question. Okay, so let's get started. Okay, so our first question, if we look at our question paper, 6 marks. All of these were quite large mark allocations. Prove the following trigonometric identity. And so there's the trigonometric identity. It was simple, straightforward application of theory. The first one is just compound angles. In other words, sine of 60 plus theta is sine is same sine, different same sine, different, is it? Yes, same sine, different ratio. So it's sine 60 cos theta, same sine, plus different ratio. So sine cos, that's the different ratio. So this one is cos sine. So cos of 60 degrees, sine of 30 degrees, theta. And then minus, and then remember, when I substitute, when I apply something and there's a negative in front, just keep the bracket so that we can remember to distribute the negative. But cos is, if this is same sign, different ratio, this one is different sign, same ratio. So starting with cos, we've got cos of 30 degrees, cos of theta, and then if this is a plus, it's cos is different sign, same ratio. So minus, if that's a plus, this is minus, and then sine of 30 degrees, sine of theta. Okay, and so what we had to do, sorry, I don't know if I read this, prove the following trigonometric identity. In other words, prove left hand side is equal to right hand side. And so on the left hand side, I can now use my special angles. Sine of 60, I'm not going to go through all of that. You should know sine of 60 is square root 3 over 2. There's a way of determining that, but without a calculator. Cos of theta plus, and then cos of 60 degrees is a half. Sine theta, and then minus cos of 30 degrees is square root 3 over 2. Cos of theta, which is great because that's going to get rid of this, and then the negative means it's plus. Sine of 30 is a half sine of theta. And so in simplifying this and this is going to cancel, and then a half sine theta plus a half sine theta is just 1. If I have a half of this and a plus another half, I just get sine of theta. Okay, so that's the left hand side as simplified as it is possible, and then the right hand side I just have tan theta cos theta. So this was the left hand side. On the right hand side I now have tan theta times cos theta, and this is actually just the standard. If you just wrote that this is equal to sine theta, you would have received full marks, but tan is sine theta over cos theta, and so now we see the cos thetas just cancel. Okay, and that leaves me with sine of theta. So as you can see, there was nothing complicated. This was a level 2 question. Now granted, it was a lot of steps, but none of it was ever difficult. It was simply applying the compound angle identities, special angles, and then eventually just simplifying on both sides until you get the same result, which was very simple, and yet very few people actually successfully did this. I don't know why. For some reason you can't apply your double angle or your compound angle identities. What I do want to show you is that there was a way to convert this expression here, and I only noticed it now. When we can change a cos into a sine, because sine of 90 degrees minus theta is equal to cos of theta. Okay, so basically what that means is if I give this a negative, I'm just trying to figure out now because I I didn't have this on the memo, it's just something I saw now. What's going to be better? You could either have that, or you can say that cos of sine of 90 plus theta. Will that work? See, sine of 90 plus theta is still in the second quadrant where sine is positive, so you can either plus or minus is cos theta, while cos of 90 degrees plus or minus theta, if it's plus theta, it's in the second quadrant, where cos is negative, so it must have a negative, positive, because cos 90 minus theta is in the first quadrant. So this changes to sine of theta, but okay, whichever. So in other words, if I wanted to go from cos to sine, I can add a 90 degrees. So adding 90 degrees is not going to help me, because then I get to 120. So what I would rather like to do is take 90 degrees and subtract it, the angle in there. Okay, that seems good. So in other words, if I have sine of 60 degrees plus theta minus, and then now all I'm going to do is take 90 degrees minus the angle inside, and that will change it to a sine theta. So I don't know, I don't think it's complicated, but I'll understand if you're a little bit confused on that step. But you could have done that, and this leaves me then with doesn't really work, it seems, because now I've got a minus sine of 60 degrees minus theta, and so it's the same really. I'm just going to apply the rule twice. So yeah, I'm still just going to apply the double angle formula twice. I was hoping maybe it simplifies to a single term and I apply the double angle identity just one, or the compound angle identity just once, but then it didn't work out, so that's fine. Okay, so let's move on to the next question. Again, really a very simple, straightforward, routine question that gives you 9 marks. But again, people just didn't apply the double angle formula. So here I give you a hint to determine the general solution, but I'm saying let y equal cos theta, cos x. So in other words, wherever you have a cos x, you can replace with a y. But here you don't have a cos x, you have a cos 2x. So before you can substitute y, you first have to replace this double angle with an identity where that doesn't have the double angle. And so if I go there, so we've got cos of x, and then in here cos of x plus 1, I think it's 4 cos x, 4 cos x plus 1 minus 2 cos 2x is equal to 3. And so this was a difficult question. I don't take that away. It was difficult in the sense that there were a lot of steps, but it was really not difficult to know what to do next. So before I can replace my y, I want to replace all my cos x's with a y, but the problem is there's one expression that doesn't have a cos x. What am I going to do with that? Most people did this. Most people said 2y, and then they multiplied the y again with 2, but that is saying that cos 2 of x is 2 cos x, and that's not true. So we have to replace this first with the double angle identity, which is 2 cos squared x minus 1, all equal to 3. So now I can replace with my y. So let's start in a different color. Keep your attention. So 4x minus 1, 2 times 2 is 4. So that's 4. And now this is just cos x squared. And we write it with cos square x. So now I just square that. Minus 1, and this minus 2 makes this a plus 2. equals to 3. And so we have, if we simplify now, we have 4y squared minus 4y cubed plus 4y plus y minus plus y. Oh wait, this is 1. That means plus 3y because this one and that one adds together and multiplies with y. Everything now has a y, an extra y distributed through there, and then just a negative 3 on that side is equal to 0. And so here, from here on, what I want to do is I'm solving a polynomial equation. And solving polynomial equations, I must find a factor, something that I can substitute to get 0. So you can see here's like a minus 4 and a plus 4, a plus 3 and a minus 3. So if I can just get rid of the y's simply, and I don't mean to say 0 because that will get rid of the y's, but I mean like if the y just didn't change anything, then it will work. So in other words, if y is equal to 1, look, then I've got negative 4 plus 4 is 0, plus 3, negative 3 is 0. So y equal to 4, that means y minus 1 is a factor. And then we just substitute that into solution. So I've got y minus 1, and then what's left over is y times negative 4. I should have actually let's just rewrite this quickly. Let's make this 4y cubed minus 4y minus 3y plus 3 is equal to 0. I would hate to have a negative in front here. So now that we don't, it's still true. Y is still a solution to there. It's just the signs have swapped. Okay, but nevertheless, we continue. And now I like the K method of solving my quotient when I divide, but you can use long division. And maybe in a previous video I did the quotient rule. So not the quotient rule, the K method. So let me do long division in this one to accommodate all of you. Okay, y minus 1. Y divides into there 4y squared. So then I get 4y cubed when I multiply it back minus 4y. This becomes a plus, and so that this is just 0. When I bring this down, it's minus 3y plus 1. Now that means that my y squared term, sorry, I lack my square, my y squared term is 0. So this is plus 0. And then the last term is y goes into there, 3 plus minus 3 times, and then 3 times y is negative 3y, negative 3, sorry, that must be a plus 3, negative 3 plus 3, that gives me plus 3. When I subtract these two expressions, I get 0. So that my quotient here in the middle is, or what's left over when I divide with y minus x, my remainder is 0, but my quotient is 4y squared minus 3. And there I've factorized. I factorized into two factors, so now I can say y is equal to negative 1, positive 1, or 4y squared is equal to 3. So y squared is equal to 3 over 4. So y is equal to plus minus square root 3 over 2. I took the square root on both sides, and then I remembered to take a plus minus. Now, yay, I'm done. I'm not done. I'm not done because I never had a y to begin with. That wasn't what I had to solve. I had to solve x. So I have to introduce x back in. So I have cos of x, because that's what y was actually equal to, is equal to 1. And here, or cos of x is equal to square root 3 over 2, or cos of x is equal to negative square root 3 over 2. Each one of these gives me a different reference angle. Cos of x equal to 1, that's for a reference angle of 0 degrees. Square root 3 of 2, that's a reference angle of 60, no I lie, 30 degrees. 30 degrees reference angle. And then the final one, this one, where is cos negative in the second quadrant? So cos of negative square root 3 would give me 180 minus 30 degrees. So it's the same, it's just where it's negative in the second quadrant. So my reference angle is 150 degrees. You could have used your calculator at this point. I don't think we said without a calculator. No. So you could have. And so from here on out, we then know, okay, this general solution would be x is equal to 0 degrees plus 360 degrees times k, or the reference angle times negative, the negative of the reference angle, because cos is positive in the first and the fourth quadrant. The first quadrant is positive angles, the fourth quadrant is negative angles. So, or you could have said 360 minus, but 360 minus or just negative is the same thing. And then this one would be x is equal to 30 degrees plus 360 degrees times k, or x is equal to negative that, negative 30 plus 360 degrees times k. And then this last one is x is equal to 150 degrees plus 360 degrees times k, or x is equal to negative 150 degrees plus 360 degrees times k. Cool. And so what does that mean? That means we're done. Okay, so as you can see, it's an incredible amount of work to do. Yes, it really is, but for 9 marks you have about 11 minutes to do it, so more than 10 minutes to do that, and we did that. Okay, then we came to a little bit of an application of Trig, and this application was in kind of like a Euclidean geometry setting. They say consider the triangle ABC that is circumscribed by the circle, by a circle. So in other words, there's circumscribed means that the circumference of a circle is drawn through triangle ABC, and then AD is a diameter to the circle that meets BC in E. So AD is a diameter that's drawn. So here's a circle. Now out of the one part of the triangle, we draw a diameter there, and it meets BC in the point E. And so now there's just a few things that we have to show. Show that AB over AC is sine C1 over sine B. So this should trigger you and you should ask, what triangle am I working in? There is a total of 5 triangles here. 1, 2, 3, 4, 5 triangles. Which one am I working with? And this one tells you ABAC. So ABAC. So I'm working in triangle ABC, and so it's very simple to, from there, just apply the sine rule, because then I just see a bunch of sines. So I could simply have said, well, sine of C1, that angle, divided by its opposite side, sine of C1 is AB, divided by AB, is equal to sine, and now, which is the other one is B, sine of B over AC. Sine of B over AC. And then it was just a matter of multiplying both sides with the denominator here, and dividing both sides with the numerator there. So, and that solved it. It was really not difficult. I don't know, people had no idea what was going on. So AC over AB is equal to sine B over sine C1. Okay, and that was what we had there. AB over AC is sine C1 over B. I think I did it wrong way around. Yeah, AB over AC. Yeah, well, would have just done it the different way around. It doesn't really matter. You only got a point for literally just writing down the sine rule. You got the point. If, of course, you could show that the sine root simplified to this, but that's really what it was about, just writing down the sine rule. Prove that, okay, so now they tell us, prove that the area of triangle ABE, the area of triangle ABE divided by the area of triangle ACE is equal to BE over CE. So BE over CE. So here we have two triangles. One, what do they have in common? Well, they have the same apex. In other words, their height, if this is the base, both of them have the same height. The A is the same height above the base for both of them. So there were two ways you could have used it. What they also have in common is they have in common this side. Here, side AE. What else do we have? Okay, so BE over CE. Let me see. Yeah, oh well, let's use both of those. So we could have said that so kind of here that triangle A, you see there again, triangle A, BE, A and ACE, ACE. Okay, there were two ways. You could have said it's just half base times perpendicular height divided by half base times, let's call it base 1 and base 2 times perpendicular height. Then you could have said perpendicular height is the same for both triangles. Okay, you didn't even have to give a reason, it's just you can see it's the same height. A is that delta 8. You could have drawn it in if you wanted to prove it to your examiner even more, but so those two values are the same, so this is just equal to a half. The base then for the one is BE and for the other one is CE, so it's a half BE for the one divided by a half CE for the other one, and this would have cancelled because they're the same value, so the same height, so the halves also cancel. You could have done that there and you've got it. It's not difficult at all. The alternative was you could have used that triangle ABE over triangle ACE. You could have used your sine rule, so you could have said or your area rule is a half and then BE. So you want to use BE and the common side. And the reason why I want the common side, AE, is so that it cancels. So BE, AE, so which angle should we use? Sine E1 over a half BC, or CE, sorry, CE, that's the base, times the common side, AE. So you see I use this side and that side, and then I'm going to use the inclusive angle. This side and that side and the inclusive angle. So sine E2. Okay, and then these obviously cancel, and so I'm left with BE over CE. And here we've got a little bit of a problem. Now these two can't just cancel. But notice what? E1 is 180 minus E2. So this is just sine of 180 degrees minus angle E2 over sine of E2. And 180 minus sine is 90 degrees in 90 degrees, is positive in the second quadrant. So this can change to sine of E2. It can simplify over sine of E2, and that cancels and obviously leaves us with the same answer. Okay, so again, very straightforward, nothing difficult there, just applying formulas. Show that A1 is 90 degrees minus C1. So show that A1 can be written as 90 degrees minus C1. Well, what can we see about A1? Well, we can see A1 is equal to C2. Why? It's angles on an arc. Okay, A1 is C1. They both come from BD. So they're angle on an arc. And then C1 and C2 is 90 degrees because AD is a 90 degree, is a diameter. So this is angle in a semicircle, it's 90 degrees. So C2 is 90 degrees minus C1 because this is 90 degrees. If I have C1, let's say it's 40, then I know this one must be 50. 90 minus 40. So that's probably how you can start. You can just say, well, C2 plus C1 is equal to 90 degrees. Angle in semicircle, and so C2 is equal to 90 degrees minus C1. So C2 is equal to A1, which is angles on arc. Therefore, angle A1 is equal to 90 degrees minus C1. So again, nothing to write home about, nothing at all difficult about that question. It was simply a straightforward answer. Now, this one was super difficult. Granted, okay, so of the 3, 6, 7, there's another 6 points that was difficult. So, all we do here first is we say that it can be shown that A2 is 90 degrees minus B1. So we have A1 is 90 degrees minus C1. A2 is 90 degrees minus B. And so now the question is show that, prove that BE over CE. Now, this is not a coincidence. BE over CE should look familiar to that. So we already know that BE over CE is equal to the area of those two triangles. This triangle over that triangle. Okay? And we also know that AB over AC, so all of these questions are now being used to answer this final question. So BE over CE, that's how we can start. So we can start by saying, well, BE over CE is equal to triangle AB divided by triangle ACE. Okay. Now triangle AB divided by triangle ACE, if we look at the picture, let's use these two sides. So we want to use the fact that A1 is equal to 90 minus C1 and A2 is 90 minus B. So let's use these two. Let's use side length AB over AE. Now let's just see, where do we want to get to? BE sine A. Yeah, well, we'll get there. If we make a mistake, then we try again. So this is a half times side length AB times AE sine A1. divided by half, and this time AC times AE sine A2. This is going to cancel, that is going to cancel, so we're left with AB over AC times sine of A1 is sine, and now we'll use our A1 was equal to 90 minus C1, 90 degrees minus C1, divided by A2 is sine of 90 degrees minus B, and then on here, AB over AC, we showed is sine C1 over B, sine B. So this is sine C1 over sine of B. And this side here is sine of, sine 90 minus, we'll change the sine into a cos, is cos of C1 divided by, and this one is sine, also changes into a cos of B, okay, because of 90 minus. And that's it. Sine C1 cos C1 is 2 sine C1, but it's not really, because sine of 2C1 is equal to 2 sine C cos C. So we need a 2 in front, so I'm just going to give it a 2 in front, but then I must give it 2 in the bottom as well. Multiply top and bottom. So this at the top becomes sine 2C1, and in the bottom sine 2B. So this is a level 4 type question, the first one in the trig section. It's the first one that actually required you to think a little bit outside of the box, and other than that there wasn't anything like that. So yeah, that's slightly difficult. There was no graph question in here, and that's it. Okay, so we've spent 32 minutes answering 28 questions, giving explanations as well. How did we do? 28 times 1.2 gives us 33. Yes, so okay, trig takes us a little bit longer, but also I did give some alternative solutions and explanations, but I didn't have to think about things because I knew where I was going. So I'll grant you, if you didn't finish the trig, it was a lot of work. The trig was a lot of work, it wasn't a lot of questions, so it's understandable that people might have not done very well, because if they missed the beginning, they lost all of the marks, all 9 marks, just by not applying your double angle. All 6 marks just because you couldn't apply the compound angle identity. If you didn't get question 1 here, you didn't get anything else either. So very few people actually got good marks for trig, and all I want to show you is that you must know your theory, and it's really just go back to basics. If you don't know what to do, just apply the basics. And this is mid-year exam, so we focus on grade 12 work. So the basics here would have just been your compound and double angle identities, and as you can see, it was used in every single question. Great, thank you for watching, and we'll see you in the next video.